Hello, in this 7 I'm going to be taking you guys through rolling motion examples. This is part 2 of angular dynamics, and I guess this part also incorporates angular kinematics, so be prepared for that, I suppose. Alright, let's start off with the first example. If I may. A hollow cylinder with a very thin wall, like a toilet paper tube, and a block are placed at the top of a plane with inclination theta above the horizontal. The cylinder rolls down the plane without slipping, and the block slides down the plane. It is found that both objects reach the bottom of the plane simultaneously. What is the coefficient of kinetic friction between the block and the plane? Alright, let's draw a diagram first. So here's our plane. Set a angle theta. And well, first for the block, it's just gonna be like this, and then here's the cylinder. So the block just has two forces on it. It has or three forces, I guess, but the normal and gravitational force are gonna combine to have one force downward there, and then there's gonna be a frictional force upward, slowing it down. And similarly for the ball, there's gonna be the gravity plus the normal force downward, and there's also going to be a friction force. And I'm drawing it here because it also points backwards, but it's also going to apply a torque. Alright. So first let's start off, if we want the two blocks to reach the bottom simultaneously, since they start at the top, they both start at the top, all we need to do is guarantee that they have the same acceleration. So we'll just find the acceleration of both. And the first object we get using F equals ma. Let's give them both, let's give this one mass m. And it's ma is equal to, well, mg sine theta. It's going to be downward. And then we're going to subtract the kinetic friction, which is mu sub k, mg cosine theta. And so acceleration is equal to g sine theta minus mu sub k cosine theta. And now we find the acceleration of the cylinder. So for the cylinder, we also have to write down a torque equation, and that gives us a little bit more variables. It gives us angular parts, but the way we relate them, the way we get enough equations is to use this without slipping condition. So first of all, let's just write down the F equals ma equation, and let's just give it mass m for simplicity. And so we get ma is equal to mg sine theta minus mu, this is static friction this time because it's not slipping, and so the bottom of the cylinder is not moving with respect to the plane. So ma is equal to mg sine theta minus mu mg cosine theta, and then the torque equation you get is going to be, if we do it about the center of mass, is going to be mu mg cosine theta times r, which is the radius, is equal to I alpha, and in this case I is going to be, since it's hollow, it's just going to be mr squared. So mr squared alpha. But actually, to demonstrate something, I'm going to add the beta coefficient that's usually here, which could be like 1/2 for a solid cylinder. And so now we have an additional alpha, but the way we relate the a and alpha here is we use v equals omega r, which if we differentiate both sides, then we get a is equal to alpha times r. So after canceling the r here and the r here, this equation is actually mu mg cosine theta is equal to beta ma. And the other equation we have for ma is equal to mg sine theta minus mu cosine theta. Oh, there should be mg here, but anyways, once we add these two equations together, we're going to get what we want, which is mg sine theta is equal to 1 plus beta ma. And we can divide by m times 1 plus beta on both sides, and we get the acceleration. And we get the acceleration is equal to g sine theta over 1 plus beta. Alright, now we need to set this equal to the acceleration of the block, and which is g sine theta minus mu sub k cosine theta. And we can cancel the g's, and if we move over some terms, we're going to get mu sub k cosine theta is equal to, it should be beta over 1 plus beta sine theta. If I did that correctly, so we get mu sub k cosine theta is equal to beta sine theta over 1 plus beta, and we just divide by cosine theta, and so it should be equal to beta over 1 plus beta tangent theta. Alright, so that's how we solved for mu sub k, but this equation, this answer I believe is not really as important as what we found right here. A is equal to g sine theta over 1 plus beta. So what this illustrates is kind of the idea that this rolling adds a effective mass of beta m. So the normal, the force pointing down the plane is mg sine theta, but if we replace it with an inertia of m plus beta m instead, then we get the equation here. So it's kind of like the rotational inertia of beta mr squared adds an effective mass of beta m. And that's one idea you can try to use to check your answers. And we'll see that in some of the following examples. And so I'd like you to take that into mind. Keep that in mind. And this is still the final answer if you want it. Beta over 1 plus beta tangent theta. Oh, and of course, if you want it for the example here specifically, we'll have beta equal to 1. So it's going to be 1/2. Alright, let's move on to the next example. This is also from the F equals ma, and this is going to illustrate the effective mass idea of beta m again. Alright, a disk of a moment of inertia I, mass m, and radius r has a cord wrapped around it tightly as shown in the diagram. The disk is free to slide on its side as shown in the top-down view. A constant force of T is applied to the end of the cord and accelerates the disk along a frictionless surface. After the disk has accelerated some distance, determine the ratio of the translational kinetic energy to total kinetic energy of the disk. Alright, so let's start off with K translational, since that's pretty comfortable for most of us. So K translational, well, first let's find the velocity after some time t, and that's just from F equals ma. The acceleration is t over m, and so after some time t, then it's going to be, the velocity is going to be t over m times little t, which is time, and so we have to square that to get the kinetic energy, which is this, and this is also equal to 1/2 t squared little t squared over m. Alright, and now what about the rotational kinetic energy? Well, we can use the force and torque equation here, and so this is radius r, so the torque is equal to t times r, which is equal to I alpha, and in this case, it's just given to us as I. So I alpha, and that gives us alpha is equal to tr over I. So after some time t, the angular velocity is going to be trt over I. So then the rotational kinetic energy is going to be 1/2 I times omega squared, which is tr little t over I squared, which is equal to 1/2 t squared little t squared r squared over I. And here we can kind of see some of the analogies of here m to inertia and t to t times r, which is torque. Alright, and so the total kinetic energy, of course, we just add these two. Sorry, I wrote trans here, but it should be rotational. And so the ratio to the total kinetic energy is going to be, you can drop the factors of 1/2, of course, so t squared little t squared over m over t squared little t squared over m plus t squared little t squared r squared over I. And that's equal to, if we simplify, I over I plus mr squared. And so that's our answer. And we can again see this sort of effective mass of beta m popping up. So if we write I equals beta mr squared, this ratio becomes beta mr squared, beta mr squared, and these all cancel. And we see the 1 plus beta in the denominator, sort of like that effective mass. So that's a really useful idea that I like to use a lot, so I recommend you try to keep that in mind. Alright, let's move on to the next example. Example 11.6. A uniform cue ball of mass little m and radius r is struck by a horizontal force F directed through the center of the ball. If the initial velocity of the ball after this collision is v0, the coefficient of friction between the ball and the table is mu, for how long does the ball travel before it begins rolling without slipping? Alright, so here's a ball. It has some velocity v0. This F doesn't really matter here because they give us the velocity afterwards anyways. And there's going to be a friction force here. And that's about it. So when it rolls without slipping is when v is equal to omega r. So we want to find the time when that happens. So let's first find v as a function of time. And that's of course going to be v0 minus the acceleration times time. And in this case, the acceleration is given by the friction force over the mass. And the friction force is going to be mu mg, since the normal force is mg. So this is going to be mu gt. And now for omega of t, well, what's the torque on here? So we get torque is equal to F sub Fr, which is equal to, well, the force of friction is again mu mg, so mu mgr is equal to I alpha, and the moment of inertia is, this is a uniform ball, so it's going to be 2/5 little m r squared times alpha. And so we can cancel these out, cancel this out, and so alpha is equal to 5/2 mu g. So omega of t is equal to, since it starts without spinning, because it's directed through the center of the ball, the omega of t is going to be 5/2 mu gt. So now we just plug these in and we want to find the time when v of t is equal to omega of t r. And so let me just go ahead and plug those in. Oh, and looks like I dropped a factor of alpha here because of course this is units of velocity when it should be units of 1/seconds. So let me add a 1/r. And so the r and 1/r is going to cancel. And now we can move over some terms and we get v0 is equal to 7/2 mu gt. And so the time when it stops, when it begins rolling without slipping, is going to be 2v0 over 7 mu g. Alright, that's that problem. And it's kind of an example of when you should sort of write down omega of t and v of t, which I find that you don't do too often in other cases. Alright, let's move on to the last example. And this is quite a similar start, I guess. A uniform sphere of mass m is placed on a long board also of mass m and is given an initial velocity omega naught and initial horizontal velocity v naught. Friction between the board and ground is negligible, but friction between the board and sphere is not negligible. What is the critical velocity v sub c such that the ball will eventually stop rotating with respect to the board? Alright, so there's actually two ways to approach this problem, and I'll present both of them because they're both just as valid and useful. Sometimes one is more useful than the other. So I'll start off by doing a analysis with by a direct analysis using force and torque. So if we have the board here and the sphere here, then well, the only force on the sphere besides normal force is the friction force backwards, or well, it doesn't necessarily point backwards, but at least it points opposite the direction that it points on the board. And say it has initial velocity v naught and initial angular velocity omega. Alright, and now we can write the force and torque equations of both the both the board and the sphere. So let's start off with the board since it's easy, there's no rotation. And say the kinetic friction force, let's say that the coefficient of kinetic friction is mu sub k, and we can write mu sub k mg is equal to, this is the board this time, mass of the board, times A. And since it's the same mass, it's easy, and it gives us A is equal to mu sub kg. So at time t, V board of t is equal to mu sub k gt. Alright, and what about the sphere? So we can write force and torque again, and for this one we get mu sub k mg is equal to ma, but this time it's decreasing, so we can write a negative here, and so we get v ball of t is equal to v naught minus mu sub k gt. And so at some point they'll have the same velocity since this one is increasing and this one is decreasing. And at that moment we also need the ball to stop rotating, otherwise there's going to continue to be a friction force between them, which means they won't eventually stop rotating. So now we need to write omega of t, and for this one we can write tau equals I alpha, and the torque is going to be mu sub k mg times r is equal to, well, this is a uniform sphere, so the moment of inertia is 2/5 mr squared, and we multiply by alpha, the angular acceleration, and we get alpha is equal to 5/2 mu sub k g over r. So omega ball of t, and in this case we're assuming it's increasing based on the directions we've written. So omega ball of t is going to be equal to omega naught plus 5/2 mu sub k g over r times t. And so now we need to, so the time t when the ball stops moving with respect to the board is when v naught minus mu sub k gt is equal to mu sub k gt. And so that gives us time t is equal to v naught over 2 mu sub k g. I'm plugging that in. We need omega naught plus 5/2 mu sub k g over r times v naught over 2 mu sub k g equal to 0. And so a whole bunch of things cancel here, and we're left with omega naught plus 5/4 v naught over r is equal to 0, and so v naught must be equal to minus 4/5 omega naught r. So in other words, it can't be moving in the same direction at the start like this, it has to be moving backwards, which would make intuitive sense since it needs to slow down. Alright, so that's the direct torque force and torque analysis, and there's a lot of equations. So here's a bit of a nicer way, in my opinion, which is to use conservation laws. So we have V naught again, omega, and the board is still. So first of all, by conservation of momentum, we need mv naught equal to mv final plus, well, at the end they have to be, they'll be not slipping with respect to each other, so they'll be at the same speed, or not slipping as in not moving with respect to each other. Of course, it could be rolling without slipping, but so we get mv final plus mv final, which gives us that v final is equal to v naught over 2. Now we apply conservation of angular momentum, and we're going to apply conservation of, well, first we're going to only consider the angular momentum of the ball, and I'll show you a way that it's conserved, because you might be like, oh, there's a net torque, it can't be conserved, but if we choose the right axis, then it will be conserved. So let's choose this axis right here as parallel with the top of the board. So then there's no net torque about this axis, because all the forces on the ball are parallel. Well, there's the normal force, but it's equally cancelled by the gravitational force, so that doesn't apply a torque, and the frictional force goes through the axis, so that doesn't apply a torque either. So we can write the angular momentum of the ball about this axis and set it equal at the end and at the beginning. So at the beginning, well, there's the I omega term, which is 2/5 mr squared omega naught, and then there's the component r cross p, which is going to be mv naught r, and we set that equal to the final angular momentum, which we know the ball is not going to be spinning, because that's the condition given in the problem, and it's going to be moving at this speed here, so that gives us mv final r, and so 2/5 mr squared omega naught is equal to mv naught over 2r. So we can cancel r here. We can't cancel the 2. Oops. But we can cancel the m here, and we can multiply over the 2, and this gives us v naught is equal to 4/5 omega naught r. So this got the same answer as before, or I guess a negative term was dropped here. It should be like that. But it's essentially we get the same answer, but it's a lot less work. But this is a lot more straightforward to think about, because you also have to find this particular axis on this one. But both are very valid, which is why I wanted to show both methods. And that's it for this example. And that's also it for this video. So thanks for watching.